Right. Okay. So a couple of things. If you haven't got kids yet, look up the names that you plan for them before you give them their names. My parents managed to do this before the internet was invented, and it turns out Kevlin Henney is internet unique, so this is useful. And I will confess to having done this for both of my kids. And when my older boy turned 13 last year, we said, okay, we'll let you loose on Twitter and all the rest of it. And he said, what shall I put down as my name? And I said, just try your name. And he tried it. And it's just like, oh, it's available. It's just like, yes, 13 years in the making, that one. So, you know, all these things kind of play out eventually. Books, pattern books. I've got my name on a couple. Are these relevant? One of them might be. It might pop up later in the talk. The 97 things every programmer should know. Just from a general point of view, I'm going to quote something from that from a couple of guys. It's a crowdsourced and open source book, so actually the original stuff is still online. We're going to do a 97 things every Java programmer should know. We're going to kick off that kind of last month, but that hasn't really been happening. But you know, if you're interested ultimately in contributing to that, please get in touch. We kind of went through, me and O'Reilly and the editor O'Reilly kind of went through. It's just, okay, so what should we pick? You know, what technology area or whatever? And it turns out that Java is everywhere, apparently. You know, still. We can't shift it. So that was the winner of that one. However, what I want to talk about is I seem to spend an awful lot of my time talking about stuff that's really old. Not just pre-internet, but really old. So this is taken from something that Tim Berners-Lee wrote at the beginning of the 90s, hence its reference to computer science in the 1960s to 80s. And he sort of stopped in the 80s. It's like, yeah, we're done with that. That's last decade. One of the reasons I end up going on about stuff that's old is most of the stuff that we are struggling with or getting our heads around, or the new ideas that we often encounter are surprisingly old. Most of them are very, very old. They have some thread that runs through history that we could probably learn from so we can, you know, try new stuff. But it turns out there's also some bits of wisdom lurking in there. They were always there, but perhaps the mainstream way of looking at things distracted us. So he said computer science in the 60s to 80s spent a lot of effort making languages which were as powerful as possible. And we can actually see from the 21st century perspective that has continued to be true. We can just put, you know, ... You know, it will always be true. Nowadays we have to appreciate the reasons for picking not the most powerful solution but the least powerful. So this goes against, and we often talk about powerful solutions because surely more is better. You know, you want more volume on something, you want more stuff on something. I'll have another drink. That's more drink. More is better. You know, so more powerful. You know, is clearly nobody's going to sell more powerless or less powerful. So you want more powerful. It's almost a self-evident truth, except perhaps it's not. And he makes the point here. The reason for this is the less powerful the language, the more you can do with the data stored in that language. It becomes easier to analyze. If you write it in a simple declarative form, anyone can write a program to analyze it in many ways. And that's a really interesting sort of proposition. And I stumbled across this design principle. It's up on the W3 and has been for decades. But I stumbled across it a couple of times. But most recently, somebody was writing a couple of years back was writing a blog about configuration files. And for Python, they were saying, well, you know, it's kind of logical that you have this stuff in Python, but actually maybe we shouldn't do because you can do anything. But do you want to do anything? Perhaps if we didn't try to do anything, the resulting data structures would be clearer, but also the execution would be more efficient, more easily parallelized, whatever it is. But because we've put it down in an imperative form, it does this, then it does that, we're less open to the possibility of getting behind that and really looking into it and saying, well, what do we want from it? What else can I do with it? So back to the 1970s, here's one of the classic examples. Make. So this is my photocopy. Is it a photocopy? No, it's actually my printout. This very simple observation that we see in Wikipedia, which we were just talking about just before this, makefile language is similar to declarative programming. this class of language in which necessary end conditions are described, but the order in which actions are to be taken is not important, is sometimes confusing to programmers used to imperative programming. This continues to be true. Now, make is the kind of the granddaddy of all the kind of build tools, and they are all declarative. If you try and think, how would I write a build tool that was imperative, it would get very boring. It's not that you couldn't do it, but you're going to spend an awful lot of time duplicating things. If this is older than that, you're going to end up, with any luck, reinventing this idea. You will eventually end up extracting all your dependencies as data structures. You will end up extracting these as rules. You will end up with the consequent actions as the little piece of imperative code that is executed. But the basic rule structure, with any luck, if you refactor fairly aggressively, you should end up there. But what do most organizations do? Not that. So this is one of the things, is this has always been there, and it's not just for things like make, but there is this idea of a different way of looking at it. These ideas have been around for a long time. So let's go back to the 1970s. Nicholas Wirth, Mr. Pascal, he wrote this book, which is actually quite a decent read, Algorithms plus Data Structures equals Programs. And it's not a bad book, and it's a very interesting principle. Classic structured programming, that's what he was talking about. What we're looking at is something slightly different. It's a very different approach. Let's actually say data structures equals programs. This is taken to its logical extreme in a language like Lisp and all the Lisp family, where you actually have this very deep truth. It's all a list. Everything is that. So this truth, again, this now actually goes back to the 1950s. It's been there all along. Is there something it can teach us from a different point of view? So again, going back in time, the Mythical Man Month, still a classic, still worth reading and rereading. And somewhere in there, Fred Brooks says representation is the essence of programming. There's a whole section entitled this. And you know, just it does obviously show its age a little bit. Show me your flowcharts, how quaint. And conceal your tables, and I shall continue to be mystified. Show me your tables, and I won't usually need your flowcharts. They'll be obvious. And that's one of the most interesting things that I've found, is even before stumbling across this quote, or re-stumbling across it, that idea that if you go through somebody's code and you start looking at the variables they're declaring, the fields that they're offering you, the things they're putting in their data structures, a couple of things occur to you. One of them is, I think I know what's going on. The other is, I think I don't know what's going on, because if I were doing this, if I were doing what I think you're doing, I would not do it like that. So immediately you're starting to grapple with the problem by trying to say, well, what's this flag doing here? Why have you got a flag here? Surely you can derive that from something else. Or perhaps I've missed something. You know, there's these ideas where you start looking for the redundant data. You're talking about the relationships because you're thinking, what can I do with it? And then you go and see the doing code, and that's a lot less interesting. You know, your eyes kind of glaze off it. So there's this idea, it's a sort of fairly deep one that goes back a very, very long way. So where does that leave us in the 21st century? There we go. One of those nasty truths. Simon Peyton-Jones, Mr. Haskell, he made this observation. It's disappointingly true. But there's an interesting side to that. If we look at it and sort of leave out the additional imperative stuff that you get in something like Excel, the sort of the VBA type stuff. If you look at it, what you're doing is you're creating a set of relationships that are evaluated, and you're creating a data flow model. And it's all evaluated. There's no major side effects. You change something, it all ripples through, and it's all sort of a glorious sort of wave of calculation. And it is to do with the manipulation of the data. It's exactly that. You don't sit there going like, well, if this cell is this, else if, there's nothing like that. It's a simple tabular form with a set of relationships that most people can describe quite easily. Now, what is interesting is when people come across declarative ideas, they often find them quite difficult, but that is not to do with their intrinsic challenge. It's to do with the fact you've got a lot of experience doing other stuff. Sometimes when you show somebody a piece of logic and you take away all the ifs, and it's just like, well, I can't read that anymore. That's because you've learned to expect ifs. When they're taken away from you, you don't necessarily see the thing that is there. And this is a really interesting approach, because a number of years ago I wrote something that was certainly not a spreadsheet, but it was based on a very data-driven model that was inspired by a spreadsheet, and everything just kind of happened. The guy who took over it went and maintained it, he sort of said, oh, I don't like the fact I can't see all the conditions. So when I actually caught sight of the code sometime later, after I'd left the company, I did get to see it again. And it was not how I left it. It had a lot of ifs, a lot of if-else. He didn't feel comfortable without making decisions. Yeah. Now, this also, by the way, gives us a rather interesting point when you start caring about metrics and perhaps over-care about them. If you look at a lot of coverage metrics, in other words, you go beyond statement coverage, a lot of them are based on explicit decision-making. And they fail miserably when you look at data, which is a kind of an interesting point. I might get a chance to talk about that one later. Okay, so let's go back to this. Let's look at a nice example of something that is a problem that in Birkhoff Margles' piece on put the mouse down and step away from the keyboard. He's not really talking about this piece of code. He's talking about the basic principle. If you are trying to solve a problem and you cannot solve that problem and you've been beating your head against the keyboard, don't beat your head any harder. Just walk away. Go do something completely different, because that is how you solve the problem. By burrowing in the same way, just harder and deeper will not get you there. So just go and do something completely different. And he talks about, and the specific example he uses to motivate is this piece of code. We've got a bit of Java here. We're going to try and parse a substring from a string that says time. If that fails, then we know something about it. It doesn't match a particular expectation. In other words, that these two are integers. Then once we've got that, we're going to go on and we're now actually going to look at the value and do some things with that. And then and there's a ... here, and we keep on going. And this feels very much like you are being the program counter. In fact, that's one of the things programmers learn. They learn to be program counters, which is slightly demeaning. Turns out machines are way better at this than we are. But you're kind of there, kind of like, yeah, and then. I can see the logic, and you feel comfortable with that. And people like to have multiple return statements. I'm not a big fan of those, because it turns you, a human, into a program counter. Yeah? And people learn to love that. Alternatively, you kind of put the keyboard down, go home, come back. Oh, yeah, that's what it is. You see, I can actually explain that one to my kids. Oh yeah, there's quite a lot going on there, but that's because 12-hour time is bonkers. That's nothing to do with the solution domain, that's to do with the problem domain. 12-hour time was sent to try us and show us that there's a better way in the world, but we've still got to tolerate 12-hour time. The point is you can go through that and you can actually walk through it and verbally describe it, whereas this, good God, I mean, I can talk about this and I can show this to my kids and walk them through it. Okay, let's talk about parsing. Oh yes, try and catch. I'm going to have to talk about that and exception models. And conversation is much, much simpler here. Of course, you can go a little bit too far with regular expressions. There is that classic saying, I had a problem, I solved it with regular expressions, now I've got two problems. But, every now and then, there's this just beautiful simplicity. It's like, yeah, obviously, that's this time model. Very, very simple, a declarative approach. And what we find is that this obviously fits very closely with our functional sort of our various paradigms, in particular functional programming, and Haskell, the source of all purity in this, or at least Haskell programmers will tell you that, in the monad of Haskell reality. Many programming languages support programming both functional and imperative style, and this is very true. There's a whole load of things that you can do and probably should do and should have been doing. But the syntax and facilities of a language are typically optimized for one of these styles. So in other words, you have to actually make a conscious high-energy effort to move your way away from the kind of the soft, comfortable core of where the language or its culture or the frameworks nudge you. You kind of actively have to resist certain frameworks at the for a lot of time and actually try and figure this one out, sort of move back from this. But this idea, coding conventions, libraries, they all move you in a particular direction. A language, particularly a powerful language, can actually cover a remarkable amount of space, and you end up only inhabiting a small amount of it. Now, there are large areas of any language that are marked "Here be dragons." That's why you don't wander out at night, okay, without appropriate pizza and coffee. But there are other territories that are actually quite friendly. You just never saw them, because they were just kind of over the hill, and it turns out that these ideas have been there all along. So we can maybe nudge it a bit. So I'll throw some Python here to sort of get this idea of what we think of in terms of reasoning about what we mean by declarative versus imperative. Because people normally just simply say, oh yeah, imperative, that's to do with side effects, and declarative is not. Yes, but that doesn't tell you how to work in it or think in it or recognize the habits that are almost invisible to you. So if I want the square of the first 100 numbers, we go through this. We set up an empty list. We set up a counter, and tradition might dictate that we begin. We have a variable called I. We set up a loop. We append to the list. We increment 1. You feel like you are programming because you have told the machine, even in a high-level language, exactly what you're going to do. You're going to lay everything out to the point that this kind of thinking has become so deeply entrenched in developers that I sometimes find user stories written with, user, we do this for the user, and the result of doing this is that the number of users is incremented by 1. No, it's not incremented. That's not a word people use in the real world. There's one more user than there was before you undertook this user story, but really you're not incrementing anything. Okay, there just is. There you go. I've just incremented the number of fingers. What? That's a bizarre way of looking at that. But it's so deeply ingrained in us, we don't even know we're doing it. But we've got 2 pieces of control here. That's side effect, that's side effect. We've set up the loop. By the time you retire, you will have written more loops than you ever need. There's something gloriously self-referential about the fact you repeat the writing of loops. Okay? Have you written enough loops in your career yet? No. I think I need a few more years of writing loops. I need to do that again. And again. And you've already recognized all of the kinds of loops that there are. There are certain kinds of loops. There's the, I want to do this to everything. Oh, I want to do this to a subset. I'm looking for something type. There's all these kinds of loops. Yeah? And it turns out you've seen them all fairly much time and again. And yet we feel the need to repeat them. In every language, it's one of the basic constructs that's given to us. Now, I can tidy this up a bit. Now, in one sense, this is identical, except that it's not. Because what we've got is something that is already more declarative. In other words, the for each construct is already more declarative. We are not in control of this. That's effectively a parameter of the loop. It's not under our control. We don't change it. Well, you can, because it's Python, you can change anything, but you're not supposed to. But there's the idea of we have a parameter. We no longer describe this as the act of incrementing something. We use vocabulary such as range, or if you're working in Ruby, you've actually got a direct range syntax. And there's the whole idea that this is not going to surprise anyone. Again, the whole idea is that perhaps we got a bit too clever and we've left it at the machine level. That's quite hard to explain to a kid. And I've tried, by the way. This is really easy to explain to a kid. That's surprisingly easy. And perhaps we don't want to program like children, and that's why we keep favoring stuff like this. But then we hit the comprehension, which is just like, loop, whatever. We've done that. I've seen that. I'm so sick to death of writing loops. What I want is a list of the first 100 squares, and this is what I'm interested in. If you look here, you have to still assemble it in your head. You've gone from being a program counter. Well done on the promotion, by the way. You're now also the memory, so you've got a little bit of an interaction there. But at the same time, look, it's the square of something. Oh, okay, and that's where the squares come from. Okay, so this is the very simple idea that we get that. Moved in that direction, this is a far more declarative approach. We have genuinely defined the fact that we want first 100 numbers. Mechanically, that ends up pretty much coming out as the same code, although, to be fair, this does actually run slightly faster in Python than the previous 2 examples. What we've done there is reinvented the intention. Now, this is not a word that a lot of people know, and given English spelling being the kind of chaotic nightmare that it is, I mean, some people sort of, always point out, that English does not have a regular system of spelling. They are incorrect. It has at least half a dozen, and that is the problem. This is a different spelling of intention. Intention, in terms of capturing intent, is spelled with a T. This is the opposite of extension, the set of characteristics or properties by which the reference of a given expression, whatever. The sense of an expression that determines its reference in every possible world as opposed to its actual reference. You see, I like language like that. In every possible world, it suggests parallel universes. I like this. And that's my maths dictionary. For example, the intension of prime numbers may be having non-trivial integral factors, whereas its extension would be the set 2, 3, 5, ... So the idea is the explicit enumeration is the extension, whereas the description of the rule, here's what I want. The declarative view is very much what we're talking about intention. And that gives rise to stuff like this. This is a set intention from which all the list comprehension stuff is taken. X squared, well, what we're going to do is we're going to select this from the set of natural numbers where this condition is true. It turns out we knew all of this all along. And that's, so in other words, this goes back to the 1970s and the invention of SQL. It's just that they managed to really, really hide the fact that it's an elegant model behind all of that noise that goes with commercial databases. But it's always been there. It's a very simple idea, and people get relatively comfortable with it very quickly. And we see these kinds of features making their way into languages in which they did not start out in. We can see this very directly in languages like C#, where Link has already had this for over a decade. But that very simple idea, it's easy to understand. Once you've learned the syntax, you're done. There's no loops in maths. Mathematicians have got limited attention span. They talk about infinities, but their attention span's at the other end of the scale. So it's just like, yeah, we're not going to waste time describing everything. So, yeah, we've got this kind of stuff. So, having been rude about Haskell programs, I suppose I ought to show some Haskell here, because this also gets us to another way of thinking. So, who's had a chance to mess around with Haskell? Okay, see, the number goes up all the time. I'm no Haskell programmer. I'm at best a tourist, but I quite like it. It's quite a nice place to go on holiday. And so there we see a very direct and simplified expression. We're going to take that. We're going to take x, range 1 to 100. Yeah, this is kind of nice. That's going to give us, those squares that we wanted. And here's another one. This is a nice bit of maths. This is just all of them, basically all the natural numbers squared. And what's great is that Haskell's happy with that as well. And you're not going to run out of memory. Haskell's quite happy to deal with infinite unbounded sets. Just don't look at it all at once. Okay? Do not stare at the infinity, because it will stare straight back at you and tell you do not have enough memory. Okay? The point is that it's okay to deal, because we're doing this declarative. I have not... In fact, one of the simplest ways of looking at it and what Haskell does is again, it's a linguistic trick, almost. It puts everything in the subjunctive. What do I mean by that? It doesn't say, look, here is, and here are the squares of all the numbers from 1 to infinity. It says, if I were to do this, imagine that I were to do this, and I were to take the numbers from 1 to infinity, and then I were to square each one, then it would look like this set. But that's totally hypothetical. This is, by the way, the easiest way to look at how pure functional languages deal with side effects. Because what they do is they say, imagine I were to do some I/O. I'm not doing it, all right? That's imperative. But imagine I were to do it. And imagine I were to get this result. And imagine I then did this after that. And you go, yeah, this is great. But it's all in your imagination. And then you parcel that off to the runtime, and the program is pure, because it never does any side effects. And you've just outsourced it to the runtime. The program's pure, the runtime is impure. And it will do the rest of the imagination and make it real. It's kind of a neat trick. Yes. So Haskell ends up coming, less pure. So there is this idea there of being able to posit this and just say, yeah, we're not going to deal with all of it, but imagine we were to. This is what it would look like. So lazy evaluation is at the heart of this. Now, where can that take us? Well, obviously you've got to get something out of it, so this is how we get our original result, take 100. Thank you very much. I will actually have that hypothetical bunch of stuff you got. I'll take the first 100, thank you very much. And I might take another 100 after that. I might take a ridiculous amount, but don't worry, I'm never going to take an infinite amount because I don't know how to actually write that and ask for it. So let's try this on a real enterprise example, Fizzbuzz. Wonderful observation from Richard Dalton. It's invented to avoid the awkwardness of realizing nobody in the room can binary search an array. Who here has done the Fizzbuzz Carter? Okay, good. I actually introduced somebody to it the other week, and I gave them the full story of it, and they said, I did not realize it was actually a drinking game. So, yeah, and actually, if you look at the Wikipedia page, last time I checked the Wikipedia page, it still has it listed. It's primarily a kids' game. And then it has the bit about craftsmanship and interview question and all the rest of it. And somewhere in there it says, adults sometimes play this as a drinking game. Citation needed. What? Being my friends, when we were younger, yeah. But I really have no idea what the incentive for kids is. And we actually tried this as a family exercise recently. We were waiting for some food in a restaurant on holiday. And we went through a number of games, and we're sitting there. And the problem is, when you've got 4 people, the youngest is 10, and he's really good at maths. The oldest is me, and I'm sober. when you've got 4 people who actually know what to do, it got really boring. Fizzbuzzes, there's no challenge, there is no joy to this, you know. And my suggestion, well, why don't we code this up on my phone, was not greeted well by the rest of the family. So let's actually look at the various ways. So let's try and take this one. Now, people often rush at this going, oh, well, yeah, Fizzbuzz, it's trivial. Oh, no, it's fun, because you can elasticate and bend your mind around all kinds of different things. And you can also use it to appreciate different programming styles. First point here. This is the most imperative solution I'm going to show you. It is very imperative because it is very much about the human being the program counter. And your running state as well. There's the result. We're going to start it off as empty. Now we're going to modulo 3. And if that's good, we're going to increment, we're going to append fizz. We're going to modulo 5. We're going to append buzz. Now, there's a nice emergent property here, clearly, is that fizzbuzz will emerge. We never have to have a special rule for fizzbuzz. But we've actually ended up manipulating the state potentially 3 times already. We're actually kind of poking it and prodding it. It's just like, if I were a variable, I'd feel, you know, slightly harassed at this point. It's kind of, leave me alone. Can you not make up your mind as to what value I should be? And then we have this kind of catch-all. Oh, if nothing's there, then let's just go for it and do a string conversion. So although it has one nice emergent property, the problem is it's actually, there's quite a lot of state being run here for such a small problem. Yeah? I mean, obviously, this is not the most horrendous piece of state problem you're ever going to see, but given the number of lines of code, although there's a certain elegance to it at one side, actually it's a bit messy. If you want to deal with something quite different, mutually exclusive options, we can talk about this in terms of being tail returns. There is every single path simply is mutually exclusive to all the other paths. Therefore, it is easy to reason about. If you've ever wondered why do you indent code, remember I made a comment earlier on about I'm not big on multiple return points. You might say, well, actually, this has got 4 return points. This has got 1. You can't understand this the same way. It turns out there's only ever, if you go down this path, you will never, there's no way you could have ever gone down any other path. If I take that return away, there's still only a single exit point. So this tail return is slightly easier to comprehend than jumpy returns. I've got to return at level 2, I've got to return at level 1. The point is all paths, even if you to take the returns away, they'd still drop off the end. And that's a very important point. Because the indentation rule, why do we indent? Well, we indent in Python because you have to. But in other languages, why do we indent? We indent because the whole idea is you're supposed to be able to ignore everything. The idea is that if you don't use a folding editor, imagine you have a folding editor, you should be able to fold everything away and still understand a high-level view of what goes on. If you have jumpiness within that and you have state modification, you're actually missing a surprising amount of the story. Okay, so there's this very different view that the indentation is to move it out of your way so you can read the spine, as it were, and get a sense of it. And that, in other words, the vision that holds true, if you've ever looked at newspaper writing, in fact, it's called newspaper style. Its formal name is inverted pyramid. Newspapers write this. The headline, unless it's in certain papers, the headline should give you the whole story. Okay, man attacked by shark. Okay, that's the whole story. There is no, that is the story. The rest of the piece will be that story, but with more detail. The first paragraph will be the man, aged, whatever, on holiday, whatever, at this beach on this day, was attacked by a mako shark or whatever. In other words, it's just more and more of the same. But you can stop at any point and you still have the whole picture. You just get more and more detail. That is how you should be thinking of dealing with method decomposition, is that as you move in, there should be a sort of inverted pyramid, and you should be able to ignore everything and still understand it. That actually has an impact for how we understand the data flow and the control flow. Obviously, don't write a long newspaper article. That's always bad. Yeah. Okay, so here's another one, which is mutually exclusive and uses just one single expression and enumerates all the possibilities quite explicitly. And it's one of the reasons I've always been a fan of the ternary operator in certain languages. Some people are freaked out by the appearance of a question mark and a colon, and I'm quite good with that. I learned those things at school, although their meaning has changed a bit. But there is the idea that these are good. I'm good with this type of stuff. Now let's get a little. So this is kind of like humdrum. Okay, I've solved the problem. Let's make it a bit more interesting. Let's try and remember, what was that stuff we were taught? Oh yeah, sets. Okay, I want a set. Let's invert the problem. Instead of trying to test the condition of something and its numeric properties, I'm going to say, look, let's do this one very differently. There's a bunch of numbers. These are all the 15s. 15, 30, 45, 60. There's all of those. Oh, by the way, there's all the 3s. There's 3, 6, 9, 12. Oh, yeah, and there's the 5s as well. 5, 10, 15, 20, and so on. And these are sets. And I want to know if a number, if we've got a number in that set, then that set maps through to Fizzbuzz. If it's in this set, if it's in the set of 3, if we've already established it's not Fizzbuzz, and if it's in the set of 3s, yeah, I'm going to say it's Fizz. So we're going to now look at that, and then this is anything that's not in that set just gets a string conversion. So, you know, same number of lines of code, but very, very different way of approaching the problem. And set inclusion is a very powerful way of thinking. And then there's another way of looking at it, sort of table lookup. This is quite fun. So what I'm going to do is I'm going to get all the fizzes. I'm going to have all the fizzes I need. Obviously, this is a little more compute intensive, but we'll get to where it doesn't become that. What I'm going to do is I'm going to take all the fizzes that I need. I don't have a fizz at number 1, I don't have a fizz at number 2, but I do have a fizz at number 3. I don't have one at number 4, don't have one at number 5. So in other words, it's basically a list that repeats 33 times. We'll have that, and this is a list, and we'll multiply that up, and we'll convert all the rest of the things. And here's all the numbers I might ever need. And then I combine everything, so it's all about the composition. I take a fizz, I add it to a buzz, and if nothing's there, I take the numbers. And it's just like, that's a very different way of looking at it. Now, that has some interesting properties, but how do I know that these are equivalent? And this also tells us one of the challenges about this style of thinking. Now, if you've written tests for Fizzbuzz, if you've done the test first kata and you've done this, one of the things you may have found is that actually getting good tests out of it's quite difficult, because you end up with very, very trivial tests, like 1 is 1, 2 is 2. Yeah, you can probably test drive your way into it, but it's fairly trivial stuff. And these are not good tests. You don't go to the test and go, yeah, these tests demonstrate a deep understanding of the problem. So let's try a different approach. What I'm going to do is I'm going to say, look, here's all the numbers. It's normally only ever 1 to 100. Because people really do give up after a while. Even human beings give up after a while. So the problem is always scoped 1 to 100. So I'll have all of those, thank you very much. And then there's a set of true statements that I need to make about them. And these must always be true. Every result is Fizzbuzz, or a decimal string. Every decimal result corresponds to its ordinal position. Every third result contains fizz. Every fifth result contains buzz. Every 15th result is Fizzbuzz. Now, most people actually stop there. If they take this approach, which is a much more property-based approach, in other words, what must be true of these things, they normally stop there, but they've fallen foul of what's called the confusion of the inverse. That doesn't tell you quite enough. You also need to guarantee that the ordinal position of every fizz is divisible by 3, every buzz is by 5, and every Fizzbuzz is 15. So sometimes we get used to the idea that there may be more test code than production code, but here it's got a little bit extreme. At least it's in Python, which means I can actually just write it exactly like that. But I've had to establish 8 truths about what is effectively 4 pieces of logic. But it's again, I've done this. That's one less plate. We've decremented the number of plates. But what we've done here is we've taken what is of value here, and granted that Fizzbuzz is a trivial problem, but what we've done here that is of value is we've taken a very different way of looking at the tests, which is a declarative view of what are the truths of this. Here are the set of truths about all of the results that I've got. And it's that idea of saying, well, let's not worry about how much that costs us. Let's actually just start there. And you can actually test first. You can actually test drive this approach, and you will end up with the same result that you expect, or any one of the ones I've just shown. You can take it property by property, and you can do this. And you know, so what we're doing here is exploring simple truths. Now, I want to go back to this. I want to pick up on something. I want to take this further. We only did 100. So what I'm going to do here is I'm going to say, here's a different way of looking at this problem. Here's all the fizzes I'm ever going to need, like all of them. In fact, more than I'm ever going to need. Here's all the buzzes I'm ever going to need, more of them than I'm ever going to need. And I'm going to combine these to be words, okay? So there's going to be fizzes, buzzes, and fizzbuzzes. And then there's all the numbers I'm ever going to need as strings, 1, 2, etc. I obviously need to choose between numbers and words. When I hit 3, I don't want the number, I want the word. Okay, I want fizz in that case. So I've got to somehow make a choice. So there's a thing called a choice. And then ultimately I'm going to get Fizzbuzz. So how do I put that together? Well, Fizzbuzz, at this point I say, yes, I've switched to Python, from Python, sorry, to Haskell. Fizzbuzz, I'm going to zip using the choice between words and numbers. The zip primitive is exactly as the name suggests. You zip together two or more lists or sequences. Simple combination is just to tuple them, but zip with basically says, look, I'm going to allow you to apply this to each one. You get to, in this case, we're going to make a choice. So we're going to take all the words, all the numbers, and choose between them, and end up with a nice list that is the right thing. Hopefully 1, 2, fizz, 4, buzz, and so on. This is the fun bit. What we're going to do is we're going to take that Python solution, but this is Haskell. We can do infinities. We need to cycle empty, empty, fizz from here to infinity. And that's just done declaratively. That's what it looks like. I don't have to compute it. I'm just going to say that's what it looks like. It repeats from here to infinity. Same idea, buzz. Full space. OK, so look, we're just, so just good job you're sitting down. That's 2 infinities up there on the screen at this point. OK. Words. Now what we're going to do is we're going to zip them together, concatenate them. So in the space of 1, empty, empty, that's empty, 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 that's empty. Fizz, empty, that's fizz, empty, buzz, and when we get to 15, that's fizz, buzz. Okay, so we've just gone and created an infinite number of fizzes, buzzes, and fizz buzzes. Okay, so that's 3 infinities. Oh, that's not enough. We need 4. Because here's all of the natural numbers. From 1, that's a string conversion. So we're going to take that, convert using show from 1 to infinity, and that will get us all the numbers we ever need as strings. 1, 2, 3, 4, the rest of it. Now all we need is the choice. Now, I've adapted, the basis of this solution was taken from the Frege, which is a JVM Haskell, a Frege page when I was talking Fizzbuzz on Twitter. And then I looked at it and I thought, I'm really unhappy that he's used an if-else. There's actually a property you can rely on. Max, it turns out that the ordering between your numbers and your strings, it works out right in the number range, in the Unicode range, in the ASCII range, whatever. It doesn't work out for EBSTIC, but that's not a problem because you'll never, ever find Haskell on a machine that still runs EBSTIC. Those things are so dead in history. Nobody's ever going to sit there and go, I know, I'm going to migrate a Haskell compiler to this COBOL mainframe of ours from the 1970s. That's a really smart idea. No, there's better things to do with your time. Anyway, people generally responded when I used Max with, oh my God, that's such a hack. And oh my God, that's such a hack. Various shades of these expressions. I like it as a hack. I think it's elegant. All good programming should have certain elegant hacks somewhere in there. But I did eventually factor it out and at least give it a proper name. Yeah? So it's a choice. That's what we're doing. So there's no logic here. This is purely, as in, it's even less than imperative in the sense that what we've actually done here is there's no decisions. No decisions are being taken. There are no ifs and elses. Nobody's telling anybody to go this way or that one or choose this one or that one. It's just a natural emergent property of how we've chosen to compose it. So I'm going to, oh yeah, by the way, we only want the first 100, so we're good. Yeah. Okay, so this beautiful observation, still true. I love functional programming. It takes smart people who would otherwise be competing with me and turns them into unemployable crazies. Now, that was true in 2009. To a certain extent, it's still true now. So let's go and look at something else. Let's look at another Carter. I run a thing, a Facebook page called Word Friday, and it's called Word Friday because every Friday I pick a word or a phrase that is unusual and I offer a full definition of it, and then the rest of the week I just post linguistic stuff and stuff that I find elsewhere. One of the nice words I came across a while back was a biquinary coded decimal, which is, obviously you're going to work out now how do I slip that into a conversation. It's Friday. I need to think of another one. I've just realized I have to do that on the train on the way home. Okay, biquinary coded decimal, a system of representing numbers based on counting in 5s, with an additional indicator to show whether the count is the first or second half of the decimal range. In other words, 0 to 4 or 5 to 9. You see this in abacus systems. It used to be used on old computers, Colossus and stuff like that. This was how, before they discovered, you know what, binary is a lot simpler. Trying to fake up a base 10 system, that's a pain in the backside. And importantly, Roman numerals. Roman numerals is the classic example of a biquinary coded decimal system, which means that we're going to do the Roman numerals Carter. Yeah? Okay, so who's had a go at the Roman numerals, Carter? You take a number, you churn it out as a row. Excellent, right. So what we're going to do is we're going to do the enterprise style. We're going to do this totally imperative. There it is. Let's change the font size. There it is. Now, if you are being paid by the line of code, this is magnificent. You will walk home with a bumper fat check. It's fantastic. But we are taking the problem as we see it. And, although this is not wrong and it will pass all the right tests, it's kind of like, we've missed something here. People have various different ways of approaching this and reducing it. And various observations, one of which is, okay, well, an if is merely a while that's executed at most once, okay? So maybe we can factor that. There's a regularity to this structure, and you can actually make it table-driven. Okay, so that's quite nice. We've now got something that is more declarative. Here's the multiples, and now I'm going to just filter through them. I'm going to ignore the fact that there were ifs and whiles, because an if is merely a degenerate while. And I've got a nice little structure here, but actually I've still got running state. So this is good. We've now factored out. We've got the kernel, the activator, and then the plug-in data, and that's quite nice. But now we're going to blitz through it. It's a case of like, okay, it's nice. Python's allowed me to keep it short. But I've got result is running up. And although value and letters are effectively parameters of the loop, I've got result and I've got number. I'm reducing number. And it's just like, okay, that's two control variables effectively. And given the size of that, that's quite a lot of activity for that, but which is good in one sense. You don't want your activity spread over a lot of space. But, because that's what happened here. But there's something missing, okay? So I quite like that as a solution, but I came across a solution a couple of years ago. As my friend John Jagger, we were messing about with stuff, and John wrote Cyber Dojo, which is magnificent, wonderful tool for pairing and just trying things out in a sort of dojo format, but with a lot of feedback. Great stuff. And he just said, Roman numerals. Have you done it, Kevlin? Yeah, I've done it in a couple of languages, and I've tried out different approaches and all the rest of it. He said, yeah, I came across this version recently, completely different approach. It's not a mathematical problem. It's not a numeric problem. See these numerical operators? It's not a numerical problem. It's a symbolic problem. If we do it in Python, it's really tidy. I'm going to take a number, I'm going to convert it to unary. I'm going to convert it to unary. So 5 is I. Yeah? Yeah, I've got the right. Yeah. That's why we don't use unary, isn't it? Yeah? Okay, and then what I'm going to do is I'm simply going to reduce it. Now, I'm not going to make any claims about the memory efficiency of this. But the whole point of looking at this stuff is to provoke and inspire a different way of thinking. It's just like, oh man, yeah, that works. Basically, we take all of these things and we reduce it, we transform it, and it's just like, wow, that's a one-statement solution. Yeah? And that's really quite nice. And it's actually, the nice thing about this, I'm going to say, I like this, but you've still got to be the program counter, you've still got to run some storage there. This one, yeah, I can see that. Again, if I have to explain it to my kids, I've not tried this one with them, but I think I'd have much better time explaining this. And it's just like, that's really interesting, because you can see whether or not it's right or wrong. Now, that ability to see whether or not something is right or wrong is interesting, because earlier this year, Rebel Labs they occasionally publish cheat sheets. So Java 8 Streams cheat sheet. And I looked at the cheat sheet, and I thought, that's wrong. Because I'm no Java expert. I haven't wasted my evenings trying to figure out everything about Java 8. But the great thing is, the great thing about this style, this approach, the transformation through a pipeline approach, is it's much easier to see what is wrong and what is right. Okay, and it turns out, and so I just read through this. Get the unique surnames in uppercase of the first 15 book authors that are 50 years old or over. We're going to go to the library, we're going to get a stream from that, and then we're going to map, we're going to select from the book, and get the... And I sort of looked at it, I said, you know what, that's not what it does. That's not what it does. If this is the spec, that's not what this does. And I don't have to go through any loops, I can actually do this. So I tweeted back a comment, and they incorrected it. Just in case you're wondering about the word, to correct is to make something correct that was incorrect. To incorrect is to take something and make it incorrect. This is still not right. Yeah? So let's sort of take this one apart. Get the unique surnames in uppercase of the first 15 book authors that are 50 years old or older. Okay, so what we're going to do is we're going to use this filter expression, or actually, no, use this map expression with this lambda. We're going to take book, which is a sum type book, and we're going to get the author. Okay, so that's got us all the authors. Then we're going to filter out any author, and we're going to filter in, sorry, any author that is over 50 or over 49. And then we're going to limit that to 15. What if we have the same author has authored a number of books? The way that I order my bookshelves is that I normally have them by author. And so therefore the first 15 books are normally going to be by one author, assuming it's a particular bookshelf. So there's a very good chance that it's going to be by one author. So therefore we're going to get 15 Terry Pratchetts, for example. Okay, because I know I have at least 15 of those. So we're going to get 15 Pratchetts at this point. So we're going to limit that to 15, and then we're going to get the surname, then we're going to shift it to uppercase, and then we're going to uniquify it. And oh, look, we've got one, Pratchett. And it's the same Pratchett. It's not two authors called Pratchett. It's the same author. Yeah, damn, we didn't get it right. Okay, let's try this. This is the incorrected version. What this one does is it gets the first 15 unique surnames in uppercase of the book authors that are 50 years or older. So what they did here is that when they tried to fix it, get the author, filter, get the age 50. Right, now we've got all the authors who are 50 or over. Now we're going to get the surname, now we're going to shift it to uppercase, now we're going to uniquify it and then limit it to 15. Yeah, that's still not what the original brief was. If you want to do the original brief, you need two uniqueness constraints. Get the unique surnames in uppercase of the first 15 book authors that are 50 years. Okay, get the author, 50 or over, unique authors. At this point, you have unique authors. Now you want 15 unique authors. Now you start messing with their surnames. But it's unique authors, then unique surnames. Now, what's nice about this is if you go back, you can actually just read all of that off. You can actually revisit and say, yeah, that's all the authors, 50 and over, 15 of them, regardless of whether or not it's the same author. That's not what we want. At this point, yeah, we're going to get everything. Now we're going to uniquify by name. That's not unique authors. I've still got the Terry Pratchett problem. And here we can actually say get the unique authors. That's what the first phrase does. From this point on, we have unique authors. Now we can do whatever else we want. If I were to show you that in a procedural imperative model, it's not that you couldn't do it. That's the point, is that with experience, that's the whole point, is you learn to read through these things. But there's a surprising amount of noise that you have to kind of get through, and you end up going through a number of loops. All the thing of interest is one level in rather than at the level of interest. So, observation, rather good piece by Brandon Rhodes on talking about Python and a few other bits and pieces. He said simple filters that can be arbitrarily chained are more easily reused and more robust than almost any other kind of code. And he gives us an example of this, a wonderful example from Doug McElroy, who commented on a piece of code, literate programming, beautifully documented by Donald Knuth many years ago. And it was 20 pages of code and explanation, very elegantly formatted because it's Knuth, so it was certainly elegantly formatted, explaining how to do this algorithm, how this worked. Doug McElroy commented on a number of bugs that there were in it, and then presented a 5 or 6 line Unix pipeline that did the same thing. And you could see that it did the same thing. That's the whole point here. You can see much more easily. So, I'm going to try another one, because guess what? Today is Friday the 13th. So in honor of Friday the 13th, one of the word Fridays that I did a few years ago was paraskevidekatriophobia. Yeah, and I'm not going to say that when I've had a couple of drinks, okay? That is a fear of the superstitious fear of Friday the 13th. Which, by the way, if anybody ever has this conversation, it's Friday, you might end up in a pub later, and you know, it's a recent thing. Really, it's nothing to do with the Templars, okay? It was invented, like most things, in the 19th century. Okay, people were bored. They discovered leisure time. It was the Industrial Revolution had kicked in, and there were certain classes of people who had enough time to make stuff up. Back in the medieval times, people simply didn't have they were nowhere near as creative with their superstitions back then. Okay, they were not numerically based. They were quite creative though. Okay, anyway, so So, okay, how are we going to find out when the next Friday the 13th is? So maybe we are deeply concerned about this. So let's have a sequence of days. Let's include only the 13th of the month. Let's include only Fridays. You can pipeline this. Okay, now you would be thinking normally, oh, I can if that and do it at condition. No, 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 there's nothing there. You can do it the other way. Get the set of all days, filter it through, boom. So this is some PowerShell that does that. Sadly, PowerShell does not afford us the ability to stretch to infinity. Damn. But I do, I'll take 500 days, that's not a bad starting point. So I'll have all the days from here to late next year. And pipe that into, I'm going to take these numbers and then I'm going to convert the number 1, 2, 3, take it from our starting point and then add a number of days. Okay, so 1 day from now is going to be tomorrow, May the 14th. So now we've got actually all our days. We've converted numbers to days from our baseline. Now we're going to filter out, I'll filter in all the ones that are day count of 13 within the month. Then all of those that are Fridays, and then we'll take the head of that. Thank you very much. We'll select the first one. And bang, we're done. We've got the, again, I'm not going to claim this is particularly efficient. This is really abusing PowerShell. But it's the idea of thinking about it like that as a kind of no-loop solution, but also in terms of sets and successive things, just taking things away, removing them. It's a very powerful way of thinking. And in case, just for a bit of fun, I did decide to sit down and do this one. I thought, can I do the Roman numerals just using bash? Yes, it turns out. I'm going to have 100 spaces, or rather I'm going to take 42. I'll have 42 spaces. I'll convert all the spaces to i's. That's my unary converter. Then I'll set it. But I thought, you know what, I'm going to really abuse the whole, I want to make this, my computer, clearly it runs too fast. I need to slow it down so I'm going to have more processes. So actually, to get the full pipeline feel, that's the full pipeline. And there's a really quite nice model there, again, of going back to this successive series of transformations. Again, I'm not recommending this one. That one does run a lot slower than that, and it runs a lot slower than an imperative version. But there's an idea here that scales. Okay? We don't do the Roman numeral thing at scale. We do other things at scale. And it turns out a lot of those can be dealt with by this sort of unbounded set idea. Okay, so here's a bunch of objects, a set of objects. They're all about objects. It's actually about psychotherapy stuff, which is, well, Friday the 13th, it's not that far away. What I want to talk about is stacks. Can there be anything we can learn about this stuff, stacks? Yeah, we can. What is a stack? It's a set of operations. Push, pop, depth, top. Okay, so that's a good start. But that doesn't tell me the semantics, the meaning of the thing. Okay, let's try another thing. Let's add a little bit more type information. A stack of type T. You can push T, you can pop, and you give it nothing. You can get depth, and you get an integer. You can ask for the top, and you get that. So in other words, pop has no side effect or rather it doesn't return a value and have a side effect in this case. So it's a very simple stack. I've got a few more signatures here. And stacks are kind of interesting because they are the lab rat of computer science. That and sorting algorithms, everything ends up talking about those. And so you can normally use it to illustrate a point. So let's try and figure out how it is that stacks work. Now I'm going to take the idea of a contract. The earliest reference I can find to the idea of an interface to something being a contract is this paper by Butler Lamson, Hints for Computer System Design. He wrote this in 1983. It's really worth rereading because if anything, when you read it, you start thinking late 80s or early 90s. If you didn't know when it was written, you'd be thinking about 10 years later. There's some really good stuff in there. And it's some of the most gratuitous quoting of Shakespeare on almost every subsection. And he said, I'm going to quote from Shakespeare. Yeah, go for it, mate. And he manages to section head everything like that. But he makes the earliest observation I've been able to find. An interface is a contract to deliver a certain amount of service. A very interesting way of looking at programmatic interfaces. He goes on to say clients of the interface depend on the contract, which is usually documented in the interface specification. You've got to love the optimism of the early 80s, it's just there. I mean, this is the era. Isn't today Top Gun Day, or was that yesterday? 30 years since Top Gun was released. Everybody had this wonderful view of what the world could be and would be like, and it was all kind of this wretched 80s music and swooping off, whatever. Anyway, this is the optimism of the past. Yeah, we don't document. So here's another thing that happened in the 1980s. The late 1980s, Bertram Meyer Object-oriented software construction. There's a glorious minimalism to this cover. There's an awful lot of content in here, most of which I now disagree with, but at the time I thought was really inspiring. And there's some stuff there that's obviously a little bit misguided. But he really worked the idea of the contract. The whole pre- and post-condition thing. He really worked that angle. That was what he was aiming for, to emphasize this way of looking at the world. So let's go and see if we can find and define the behavior of a stack just using preconditions and postconditions, without saying anything about the operation of the stack. Push, given that before is the depth beforehand, the postcondition, the depth is now whatever it was before plus 1, and another condition, the top, when we ask for it, is the same as the item we just put in. Okay, so it's one bigger, incremented, there we go. It's one bigger, and the top is the thing we put in. Okay, that seems a true statement, don't have a problem with that. Pop, whatever the depth was, and assuming that it's greater than 0, it's now one smaller. Yeah, that's also true, but it's at this point you start thinking, there's nothing, we've not said anything false here, but we're missing part of the picture. We're almost talking trivially about it. It's kind of like Plato's cave, and it's just like we're seeing shadows here, because it really gets very obvious when we hit depth. Depth. Given the result is depth, then the postcondition is that it returns greater than or equal to 0. As we've already discovered, there's an infinite number of numbers greater than 0. We have no idea which one it is. The only thing we can say is it's not negative. And that's quite trivial. I'm going to talk to a stack. Hello, we're going to have a conversation. How deep are you? Well, I can tell you how deep I am, but would you like to know the constraints on that? Would you like to know what you can guess? Yeah. Well, it's not going to be negative. Is that all you can tell me at this point? Yep, absolutely. If I push something onto you, what can you tell me? Well, I'm one bigger than I was before. That's useful. And the thing you just pushed, I've still got that. It's at the top. You see, that's an interesting conversation. This one, not so much. And the top is, we have no idea what to say about the top. The only thing we can say is you can only call this if there's something in there. And that's it. We can't even talk about that. What's missing here? It turns out that although a lot of people have got very excited by programming by contract, I got very, very excited by it. Fortunately, that excitement washed out with a good dose of reality. There's some really good ideas in there, and it's a very powerful way of thinking, but there are some deep, deep limitations. And you just need to understand when you're sort of walking through the set of possibilities, am I about to hit something that's going to end up with just trivial statements? In other words, I'm saying things that are true, but actually not very helpful. That doesn't really constrain the behavior of a stack at all. We've told you a whole bunch of stuff that it might not be, but nothing deep there. So let's take a different approach. What we're going to do is we're going to borrow from another book that's got red and white on the cover. Tony Hoare's Communicating Sequential Process, CSP. What we're going to do is we're going to look at the stack as having an alphabet, a conversation. What can we talk to the stack about? And he calls it an alphabet. He's talking about processes. What kind of things can they say? Okay, push, pop, depth, top. Okay, that's great. And what conversations can it have? Well, here is the set of all conversations you could ever have with a stack. You could say nothing to it. You could push something to it and then discard it. You could ask it its depth, then discard it. You could push, then pop, then discard it. Push, then ask for the top, then discard it. And so on and so on. As you can see, it goes on forever. Yeah, if you want to pay an intern to do this, go ahead. It's going to take a really long time to enumerate all the possible conversations. It turns out this was a solved problem. It's that. It's a state model. We can sit there and say, actually, this is the one that we're interested in. This actually tells us an awful lot more. This is a declarative model. It just doesn't happen to look like the ones in the code, okay? Because our code has come from a very different place. But this is what's going on. It allows you to generate the infinite set of possibilities that we had before. Now, where am I going to go with this one? What I'm going to do is I'm going to say, the one thing I can do is I can write a test. And the reason I was originally motivated to do this is because every time I see people do a test-first version of a stack, it always sucks. Now, I'm going to say that it's not that this doesn't suck, but I think it sucks less than most of them. Yeah? Let's rearrange things and then drop it out. Right, stack spec. A new stack has no depth. A new stack has no top. An empty stack throws when popped. An empty stack acquires depth by retaining a pushed item as its top. A non-empty stack becomes deeper by retaining a pushed item as its top. A non-empty stack, on popping, reveals tops in reverse order of pushing. Now, the wording there is already going beyond. All of those pre- and post conditions are still true, but what this now includes is history. What I'm able to do is actually see that when I push 1, 2, 3 onto it, that I get 3, 2, 1 off it. And in other words, it's now got history sensitivity, which was not available in the original interface. So the reasoning, pre- and post condition thinking is incredibly powerful, but the reasoning is not visible in the code. And that's the idea here, is that this is the closest I'm going to get to a declarative approach, is stepping outside the code itself and using examples in this case to make certain points. Here are the properties of the code that I want to emphasize to you. But the pre- and post condition model is not the right declarative model. Okay, so this is all about logic. What am I going to say about that? No, I'm going to skip a couple of slides in the interest of, that's all very interesting. That's also very interesting. This declarative approach, there we go. This is how requirements used to be. And then people discovered use cases, but they didn't discover them very well, so they bulleted them. Sometimes they numbered them. Then people said maybe we should have structure to our use cases, trigger, precondition, sequence, postcondition. And then people realized that newspaper ordering was much easier to read. So therefore, what you do is you put maybe the precondition up here or maybe down here, rearrange it, and what we've got here is people don't bother reading this bit. This is the boring bit. This is the bit where people, sitting there going like, okay, this is the requirement. This is what must be true beforehand. This is the event that causes the use case to be engaged. And this is the postcondition that must be true afterwards. And because you're using English, or in this case Latin, because you're using spoken language, you can step outside the system, and it allows you to make these universal statements about history that are not actually available to you. So that's where it can be very powerful. Now, we know people don't ignore that, but these days people say, you know what, use cases, that's so, I don't know, 1990s. I'm all 21st century. Yeah, see the difference there. It's like, wow, yeah, we've just got, that wheel there just wasn't the right color, okay? We're just going to change the words a little bit about how we talk about it. So this declarative thinking has made its way all the way through. We've gone from a very imperative model, and again, we kind of keep rediscovering bits and pieces, and then eventually we have to relabel it to make it acceptable. Now, as this observation is, this all ties back to the logic. And Tony Hoare, in fact, he gets 2 mentions here. Tony Hoare, it's a Hoare triple. What must be true before? The thing you're interested in, what must be true after? Very clear reasoning, but that's what given, when, then, in essence, is. Okay, so I'm going to close with just one more obvious consideration. When we want to understand that, there's lots of different ways of looking at things. Sometimes a very purely logical approach. Sometimes we need to think in terms of alternative systems, and I think sometimes we get stuck. So in other words, logic, very important. Pre- and post conditions, very important. But sometimes we discover that we cannot say everything we need. In other words, I want to prove the stack interface by saying things that are not available to me in that, but I can use them in English. Maybe I have to step outside it. The test case gives me that kind of historical context I need. It gives me something else. But even when dealing with the logic stuff, so here's the man famous for the Boolean data type. Although he didn't sit there in the middle of the 19th century going, I'm going to invent a new data type. Here, Babbage, have you heard about this? It's a great idea. Forget your numbers, okay? I've got something better than this. And in truly Victorian style, we have this magnificent title. These days, people just refer to his book, The Laws of Thought. But back then, you had long titles. An investigation of the laws of thought on which are founded the mathematical theories of logic and probabilities. These days, it would probably be thought distilled or something like that. Yeah? But this is how people kind of thought about it. Now, there's this really interesting idea that in terms of reasoning, how people used to approach this, and George Boole, very much a product of his times, in the 19th century, you had kind of like this post-Enlightenment, Industrial Revolution thinking. There was this idea that mechanical engineering was the way of the future, and this whole electricity thing was looking very, very exciting, and increasingly so, and everything could be solved. We had understood everything. The nature of the universe, planets have been discovered through mathematics. We've got this one sussed. Humans are logical, rational creatures, and it is only society that messes us up. Close, but not quite. This is a good book. Gary Marcus, Kluge, The Haphazard Evolution of the Human Mind. Are human beings noble in reason and infinite in faculty, as William Shakespeare famously wrote? Perfect in God's image, as some biblical scholars have asserted? Hardly. It turns out that was completely wrong. It turns out we're an absolute cognitive mess. And culture and education teaches us logic. We are not intrinsically logical, so we come at it the other way round. Now, why is this important? Because you're sitting there thinking like, yeah, I can code. I totally know logic. Right, yeah. So here's an example I've been using for many, many years, and I still use it. It's trivial as a piece of logic, except that people still struggle with it. When is a year a leap year in the Gregorian calendar? And normally people will remember, oh, every 4 years. Some people remember every 100, then people kind of, and then whenever I ask people, they normally kind of taper off. It's just like, it's really interesting because they get slower as they describe it. It's every 4, then every 100, and then is it? There's a question mark as they approach the third part, if they remember there is a third part. And they're not always sure. Is it 200, 400, 1,000? You know, is that the extra rule? In other words, this is not a big problem. It's not a hard problem, but it is one that we struggle to express and remember. If you just wander out onto the streets and just ask anybody what the leap year rule is, they'll probably run away from you screaming, get away from me, you mad person. But they will probably not remember the whole rule, and yet it's not that hard. So how do we test this? Well, if we try and do this, what's the postcondition? That's the postcondition. The year is divisible by 4, and it's not divisible by 100, or it's divisible by 400. That's the postcondition. There's only one problem with that. It's also the implementation. Every now and then, you will hit a problem for which the declarative way of reasoning about it is exactly the same as the test you might want, or vice versa. And it turns out that that's the hardest thing you can do. In other words, this test is really hard. The implementation better be a lot simpler. So simple, you can just copy and paste it from the test. No, don't do that. Okay, so this is one of those cases. You just need to learn to be sensitive to these cases and say, well, I've now got this, and I'm putting this up here because this, as people get increasingly interested in functional programming, they become increasingly interested in property-based testing, which is a very powerful way of looking at things. But it turns out that property-based testing can sometimes, if you're not aware of it, lead you down this path, where you end up doing this. And it's actually, you need an example-driven approach at that point. So there's this idea that you need to balance between these two things, to draw from two pools. To quote Emile Auguste Chartier, there is nothing more dangerous than an idea when you have only one idea. Okay? And some people I find at the moment are busy switching from the one idea they have firmly and deeply held for a very long time, throwing that away and say, oh, that was nonsense, that was in my object-oriented TDD youth, I'm now going to move to a functional nirvana and everything will be, yeah, you know what, you're just about to make some of the same mistakes that everybody else has already made, but feel free to do them for yourself. So I'm going to leave that one there because there's a few other things that we could do, and I'm not going to explore the tests. I want to leave it with Susan Sontag. This is kind of the motivation. This is kind of mirrors the Tim Berners-Lee observation. Our task is not to find the maximum amount of content in a work of art. Our task is to cut back the content so that we can see the thing at all. This is what we want from any programming style, any programming approach, any framework, any architecture. What you ultimately want is not to become subservient to it and being, oh, I'm the new program character. Hi, I've just joined on Monday. You want to be able to say, I'm able to use things, some of those come from up here, that allow me to tease away all of the noise and then express something that is surprisingly and almost dangerously simple, and yet you can see it, and there it is. And if you look at some of these, you know, I know that some of them are toy solutions, but some of them are just really, well, that's it? Is that all there is to it? And sometimes they're embarrassingly so. And you start getting other problems where you see large amounts of code just disappear. And I had this with one client where I had experience, again, it was a very declarative approach. I said, well, if you just think of this as something that's, you know, for which there is a large set of numbers that's a continuous stream, and you looked at it like this and so on, I understood what they were doing, but they were approaching it as a programming problem, lots of state, lots of threads, lots of locking. You've got to have that if you're having threads. And they reckoned about 9 to 12 months of work. And after a few days, I understood what it is they were trying to do. And I said, you do realize you could write this in just a few weeks, and you could probably do it using a shell script. And they were kind of like, no. And I said, well, look, here's the problem. And you reframe it, and it's suddenly a really simple problem, which will take a month to a month and a half at most. But do you know what they went with? They went with the 12 months. because they were comfortable with it. And that is one of the most human things that they could have done. And it was almost inevitable. As I got on the plane, I kind of knew they were not going to take any of my recommendations on board because it was too different. But they all stem from exactly this kind of thinking. I can just reframe it. Oh, and they said, yeah, we're going to run this on big servers. And I said, if you do this right, you could run it off a netbook. And it will take you 6 weeks to write and 2 developers, not a team of 4 or 5 and 1 year. But that is not the way that people deal with their comfort zone. Okay, so I just want to make you slightly more uncomfortable, or if you thought you knew declarative, take you a little bit further in an odd direction. Okay, so I hope that has been, I don't know if the word useful is right, but you know, at least thought-inspiring, or a better thing to do with your lunchtime than you might otherwise have done. And the food was great. But do you have any questions, thoughts, reflections? Oh, clapping's good. I'm good with that. Thank you. Yeah, I can throw these around. Yeah, so that's not a problem.
I do have one very just quick question about some of the solutions that you arrived to through this approach. I wonder if in a sensible team trying to work on stuff, you don't know who's going to be looking at this code maybe 6 months from now, will they understand it as well as they might do? It might not be as neat a solution, but the other kind of more, you know.
Yeah.
You got to get what I'm saying. It's like, is that as maintainable, readable, understandable? Doing it this approach, are there dangers that we need to be aware of?
Yeah, I think there are dangers, or rather, there's pitfalls because the key word understanding is there. That's the whole point. Is that, but the funny thing is that some of these things they are not necessarily. In some cases, they are much more maintainable, even when you don't understand them. So every now and then we come out with these solutions. So if we go back to just the 12-hour problem, 12-hour time, that regular expression is more maintainable, even if you arrive at that going, I don't know what this is. Well, let me just give you a quick, the time it will take me to explain the necessary subset of regular expressions versus the time it'll take you to keep revisiting and just trace it. Is that actually correct? And the other, so there is a trade-off there that in some cases these are elegant, profound, and profoundly weird. In other cases, it's just like, actually, that's really quite simple. It's more unfamiliar than anything. Or maybe it takes me twice as long per line to understand, but I've got 1/10 of the number of lines. In other words, there is a trade-off here, and it's that idea that there may be a slowdown with the unfamiliar. But the question is, if you end up with a solution that's the same size and it's unfamiliar, then that sort of dividing line, you're on the wrong side of it. But if you end up with something that is small, yet novel, and unfamiliar, then it will take you far less time to start from a standing start, say, I don't know what this is, oh, now I know what it is. You'd still be trundling through as a program counter on some of these other ones. So yeah, there is a trade-off, and you do have to be sensitive to that. And that's why I was kind of hinting at with some of the more testing side of things, that logic is good for this, but maybe not for that, and so on. You've got to try and see where that boundary is, because otherwise you will end up producing cryptic stuff.
I wanted to follow that up with a question about test-driven development and these solutions. Sometimes you look at those solutions, which are the really neat, elegant ones, and you describe how they're actually more maintainable. They almost look like complete solutions. It would be very hard to iterate towards through a sequence of tests. Whereas the other code is clearly the result of checking lots and lots of tests and then writing more code to get to it. So are these solutions one that you get to as a result of refactoring towards them, or do they basically come baked as the final solution? It's very hard to test drive towards those things.
I think they can all. I think I'm going to say that. There is a word that I've forgotten, and I think I used it the other week. Damn. Okay, I'm not going to go and look it up. But the idea of being able to arrive at the same solution via multiple different, the end state of a system can be the same regardless of the route that you take through it. So sometimes you will take a particular view and then refactor and say, oh, now I've got something that works. Now, if I just take a step back and refactor with leaving the test as is, that's my kind of safety net, my constraint. I mustn't step outside that, and now I'm going to work towards a different solution that occurred to me over lunch or whatever. Then you might do that. On the other hand, sometimes you will just take a different route to start off with. You might say, well, what kind of problem is this? I'm treating it like a mathematical problem, but actually it might just be a string organizational problem and a string manipulation thing, and actually maybe look at it like that. In fact, one of my clients, it wasn't quite like that, but they ended up with a remarkable amount of code that was in Java for what was effectively quite a simple problem that if they had used a scripting language, because it was just, I said, it's all string manipulation, and Java is not where I would have chosen. Given you had a choice, an arbitrary choice, I would not have ended up there. But because you have tests around it, you could potentially replace the solution in its entirety. But somebody else might well have looked at it and said, the nature of this problem is string manipulation. I won't start there. So it's a bit of both. Sometimes you might continue with your, we pick up a set of heuristics over time. We learn these little shortcuts and techniques. I'm doing this. Well, now's the time to kind of generalize that into a loop, or now's the time to factor that out into a private method. We have all these little helper techniques in our head, and perhaps the other way of looking at it is add to these. Just take a different route. That thing I always did first, I won't do it first. That thing I always do at this point, I won't do it like that. I'll take this view. I will add a very different test to the one that I did, which is why I think sometimes these katas are quite interesting if you do them back to front, or start from a completely different position. Even something trivial like Fizzbuzz, actually watching a group of people in the room doing it with Cyber Dojo is really interesting, because some people go for the fizz first, some people go for the numbers first. And some people generalize at different stages. But the same is also true of a larger system cutting across multiple levels of an architecture. It's like, well, which bit am I going to go for first? And it's slicing it differently. So I think that it's a different set of TDD habits, but I don't think it is different to it, if that makes sense. Any other thoughts, reflections? Yes?
So one of the arguments that I heard sometimes against, or at least as for systems to look into generative testing, is that it's difficult to find those properties while trying to figure out how to test it.
Yes.
Do you have any recommendation on the process to do that, or any?
The observation you make is completely true, which is why I don't think it's an easy one to solve. I think you just have to kind of approach it from 2 points of view. How else might I do this? At every single point, how else might I do this? How might I have done it differently? Or get another head. It turns out other people don't think identically to you, especially if you don't talk to them too much. And programmers are pretty good with that. So there's the idea of get another point of view, because sometimes you need to look at it and say, is that the right property? I've got something here that I'm happy with the code, but I want flexibility in the code, so I'm now driving it the other way around. But it can be very hard sometimes from a property point of view. People do miss out properties that are actually essential, whereas sometimes an example-based view can take you again in the right direction, but it doesn't give you the depth of meaning, as it were. Here is a truth about my code that is deep. So having both on both running in your head at one time is quite good. But I do find it's sometimes easier to think in terms, start off with examples, then generalize and say, hey, that's funny. These are all kind of grouping together like this. I can generate a category there. And do it like that. So I don't know if that's universally useful, but I tend to take the idea of, single example for a case, another single example for another case, beginning to learn how they are different and what ways they might be the same. And where my third one comes from, is that a variation of this? Or, maybe it should be grouped together. Actually, these are all this category. Now I'm going to data drive this bit. Do it like that. But some people have a different approach. So I'm not going to say theirs doesn't work. They may have better and deeper experience on that than me, but I would say you have to kind of go at it with that idea that you need more than one idea. Any other thoughts, observations? I can make one observation. Clearly not as many vegetarians as one would normally get, because the tofu sandwiches, there's a whole stack of them there. Yes?
Like computer programming is cool, take extended language, that's never a function.
Yeah.
So could it be also a reason why you find it hard to understand functions programming?
I think a lot of that point is it's what's called a path dependency. In other words, where we've ended up is very much dependent on the route we have taken, and the route we have taken is very much, I mean, my own, it doesn't matter that I was doing maths at school, and it was, it was the fact that my maths teacher sort of said, hey, here's computers, and what did I do? Z80 and 6502 assembler and basic. And yet a maths teacher, these days we would actually consider that probably a crime, because it's just like, it's so impure from that perspective. But it's just the fact he was such a geek. But it's that idea that that's the route that we have taken. In other words, people have come up through, historically, you didn't get very far without learning assembler. And even when people don't learn assembler, they have to learn enough about it and around it, and it's just like, oh yeah, this is how computers work. And again, it's a very imperative model as it's given to us. And then the languages that we learn, even if we don't know any of that, the idea is that, in the same way that everybody's still using on a daily basis loads of words from Latin, even though you don't have to have studied Latin, it's left there in the trail of our history, and that's the idea. It's like, okay, here's a language, and it's imperative by default, and this is the way we're going to teach you to program. Every book that you pick up, pretty much on how to code, starts with that premise. So I'm going to say that I think the main challenge, I don't necessarily know that functional programming is the solution to everything. Again, I'm definitely in the Emile Auguste Chartier crowd. You need more than one idea, because different problems have different shapes. And some of the choreography that functional programmers use to get around side effects feels a little contrived at times. And what I want in that case is a disciplined model of state. I don't want to pretend there isn't state. Just imagine there's no state. Sometimes it's actually easy to say, look, we've got state, we're good with that, but we've got a very, very rigorous and disciplined model, strong immutability, but very clear transformations, and so on. And these are the areas of the code that are modifiable. There is that, but still by default, that's not how we're teaching people. We are definitely teaching them, here is either the language that's going to get you a job, or here is the language that has been described and prescribed by the syllabus, or whatever, and they are almost always, even if they have good declarative properties and are still imperative, they start off with something fairly imperative in terms of their examples.
But the idea of computers programming being imperative by nature is
yeah, I don't know. I don't know necessarily that it is. I think it's imperative by history. If mathematicians had it, yeah.
Is it a coincidence? Because assembly language is heavily based on hardware, on how electronics works, which was what constrained assembly language really, and so it couldn't have been anything other than imperative.
Certainly back in the 40s and 50s and 60s, that's certainly very true. But as time has gone on, what people code is very far removed from that. There's has anybody ever seen the Linux running in a browser, Fabrice Bellard, JS Linux? It's a subset of Red Hat Linux. There's JavaScript, Intel emulator, and so the Red Hat is running on top of that, which is running within a browser, which has probably got a JavaScript optimizer, which is dropping it into native assembler. You might be running that within some kind of container, virtualized container, so it's actually running on a different processor architecture. And then by the time you actually hit the chip, well, we haven't even got to the firmware yet. In other words, we are so far removed from the original electrical engineering view. When you program, you're not programming the computer. What do computers care about? They care about L1, L2, L3 caches, instruction pipelining. None of my programming languages give me access to these constructs. So the one thing I know I'm not doing is programming the computer. So I think we have moved to a level that if we hit the reset button tomorrow, the model of computing that we came up with, the model of programming we came up with, would probably look quite different. I'm not saying it would be pure functional, but I think it would not be quite as overtly imperative. I think that would be, that would be the case. But we are where we are because of where we've come from, and I think that we're still in the shadow of that history.
Going back to your team Berner's code about looking for things that do less.
Yes.
Is that sort of an argument against things like Java, for example, that has pretty much, because it's like that code that says if it's a valid syntax, you'll probably end up in your code base.
Yeah.
Somewhere.
Yeah, that's right. Yeah.
Is that a case against going for things that give you all that power? Because out of the Tarpin paper, they say like power corrupts. If you get if you get that power to mutate this thing and do this thing.
Yeah.
You're going to do it.
Yeah. Is it a case against it? That's a really good question. I don't have a very simple answer. And certainly I don't have an answer that I could also hold my hand on my heart and say it's a true principle and I abide by it. Because hell, look, I still do a lot of C++ as well as Java and stuff. It's just like, yeah, I'd be hypocritical to say otherwise. So I'm definitely going to take a postmodern view on that. But I think there is a case for looking at language evolution a little more carefully. I think that the problem that we have is that as people get better ideas about things and how things should change, so Java now looks really different to Java 20 years ago. I mean, even Java 10 years ago looked different to how Java looked 10 years before that. Java 10 years ago did not introduce auto-boxing and stuff like that, which is totally at odds with James Gosling's original design vision. He had a very simple view of what should be available, and everything was very, very explicit. And then basically Java 5 came along and said, do you know what we said about explicit? Forget it, there's magic. And then Java 8 came along with a different programming model, and what you end up with is a language that, although has been designed by humans, also shows the fact that we end up with a lot of history. So in other words, the latest, greatest idea is this, but I can also put it into the investment of our existing code. And that's the thing that holds us in place, is the existing code. And so therefore, the power is kind of needed. But then there's also these side effects. If you take this medicine, expect some surprises, like, legacy code. Anything that is possible within a language will ultimately appear in a code base, exactly as you said. And it's just like, that's the kind of pill you have to take to get the other bit. We still want to use that code base because it has stuff that we need. So, I think that one goes both ways. Again, if we hit the reset button, actually we'd probably reinvent the same mess, to be quite frank. We are very human. But I think there's a good case for when you look at how languages are going, because they do get tugged. And you can push things or pull them in one way and say, actually this it would be really helpful if we had more of this. And that's what we see with the introduction of streams and lambdas and things across a number of languages, is that enough people have kind of pushed for that it's happened. It kind of was always there, but we kind of pushed it. So that's the new direction, but it means it gets you accumulate in a language. You never eradicate, you accumulate. So, it allows us to be experimental, but the problem is that the lab still looks like we ran all the other experiments in it as well. Okay, right. On that note, I'm going to suggest finish off the sandwiches. Yeah.
Yes. Massive thank you.